Late August 1944. 06:15 hours. Observation Post 4, coastal France. The faint light of dawn bled through the mist over the channel. In the command bunker of Flak Regiment 155W, German technical officers huddled over freshly printed intercept logs and radar charts. The numbers were impossible. On that night, 82% of V-1 flying bombs were claimed destroyed before reaching London. A lieutenant cleared his throat, voice trembling. Herr Kommandeur, these figures flout every gunnery table in the right. Another officer scrolled through shell logs, eyes widening. Burst patterns cluster around the missiles, not behind, not beyond. This defies our predictions. Commander Max Volk read through last night's reports. Radar tracks showing incoming V-1s, then sudden shell detonations in close proximity, followed by radar silence. His jaw clenched. Across his staff, faces mirrored disbelief. Each day, the gap between theory and observation widened. Germany had debuted its Vengeance program in mid-June 1944. On June 13th, at 04:25 hours, the first V-1 slammed into East London, in Bow, destroying a railway bridge and nearby homes, killing 6, injuring many more. These pilotless missiles, powered by August Pulsjet's 109-14, cruised around 640 kilometers per hour, 400 miles per hour, at altitudes from 600 to 2,700 meters. Packing warheads of 850 kilograms, the German leadership believed the V-1 would terrorize Britain at low cost, projecting power with a weapon that needed no pilots. Before the secret of proximity fuses, German engineers predicted interception probabilities based on direct hit or contact fuses. Their models assumed that 8 guns would need pinpoint timing and aim. Even then, success would be rare. Some German estimates held that the odds of a shell hitting a V-1 were as low as 1 in 10,000. Thus, when flak sectors first reported kill rates of 17% in June, those were alarming but still within plausible error margins. But as July and August progressed, those numbers climbed to 24%, then 60% by August 23rd, and 74% in the last week of August. Eventually, one dramatic day saw claims reach 82% across the coastal gun belt. These figures, cross-checked among radar posts, gun logs, and observation stations, painted a pattern the Germans could not ignore but could not explain. What the Germans did not know utterly was that Allied engineers had perfected a top-secret device, the VT variable time proximity fuse. This electronic marvel allowed artillery shells to detonate when they neared a target, rather than requiring direct impact. The origins were collaborative. British scientists like Joan Curran had experimented with radio proximity concepts but lacked scale. In the US, Section T under the NDRC took over and partnered with Johns Hopkins Applied Physics Laboratory. Physicists like Merle Tuve and liaison William Sterling Parsons drove development. Testing began early. By January 1942, prototype VT fuses were being trialed over water ranges. After successful tests, mass production was authorized in mid-1942. To preserve secrecy, early use was restricted to over-water zones, so dud fuses would fall into the sea rather than enemy hands. By war's later years, U.S. Navy documents claim 40,000 fuses per day production at peak. Parsons himself orchestrated deployment of VT fuses in naval and land contexts. The total wartime output exceeded 20 million VT proximity fuses, with corporations like Crossley responsible for roughly 24% of that total. Secrecy was ruthlessly enforced. Even high-ranking officers who saw shells in action were barred from understanding the internal electronics. German intelligence, lacking any captured fragments or hints, remained blind. Traditional AA fire demanded perfect prediction. Shells had to explode right where the target would be. Misses were wasteful. But with the proximity fuse, a shell passing within meters of a target would sense the reflection of radio energy and trigger a detonation, dramatically increasing hit probability. Turn 0, search 1. In combination with radar fire control systems like the SCR 584 and gun directors, VT fuses turned coastal gun belts into lethal funnels. Before VT, estimates suggested that thousands of rounds might be needed per V-1 kill. After deployment, that figure dropped to as low as 100 rounds per kill in many cases. In Britain in summer 1944, VT-equipped AA guns were introduced into the defense grid. Over 4 weeks, kill rates rose from 24% to 79% in sectors using VT fuses. In one documented instance of 104 V-1s detected approaching, 68 were destroyed by VT-fused shells. Only 4 reached London. By late August, the coastal gun belt had become nearly impregnable in many sectors. Yet to German ears, this rise in effectiveness seemed like miracles, improvisations of crews or radar improvements, not the hand of secret technology. Morning briefings at flak HQs were tense. Maps annotated with V-1 tracks, shell burst locations, and radar gaps raised urgent questions. Technical officers compared logs. Sometimes more bombs claimed destroyed than were launched. Bursts clustered not in trailing arcs, but side to side, as if shells intercepted laterally. Yet no captured shell fragment ever hinted at electronics within. Some German scientists attempted rational extrapolations, perhaps improved gun crew training, better radar tracking, or more disciplined convergence zones. But none dared consider that their enemy had harnessed miniaturized radio electronics inside artillery shells. Electronics Germany believed were impossible under firing acceleration stresses. Confidence faltered. Reactor-level labs, even at Peenemünde, ran tests on proximity concepts, but could not scale them. German attempts to build radio-based fuses had repeatedly failed. Challenges included vacuum tube shock survival, miniaturized batteries, component ruggedness. None ever reached operational deployment. Amid this crisis of understanding, Volk's command posts continued to receive data they could neither refute nor accept. There was no instruction from Berlin to shift tactics, because the generals had no clue what to shift to. Inside coastal radar rooms and artillery forts, dawns were different now. On that fateful day when 82% of V-1s fell victim to AA fire, the results were immediate. Streets of London saw fewer craters. Civilian air raid warnings diminished. In the battered city, many wondered whether the terror campaign was faltering. At Flak HQ, reports arrived. 104 V-1s detected near the coast, 68 destroyed by AA, a handful managed by fighters. The rest fell into the sea or failed mid-flight. German tracking posts reeled as their expectations of loss were inverted. But among Allied command, the success remained covert. The secret had to stay hidden. They celebrated in silence. For Britain's AA command, the 82% day was confirmation. The proximity fuse had changed the calculus of air defense forever. August 1944 to early autumn. The anti-aircraft belts around Britain and the Channel stood on a new pillar. Electronic fusing. But behind that pillar were thousands of men, hundreds of factories, and a machine so delicate it seemed impossible to survive a shell's launch. In cramped labs at Johns Hopkins Applied Physics Laboratory, physicists and engineers bent over vacuum tubes, resistors, tiny coils, and test circuits. The men of Section T, under Merle Tuve's leadership, wrestled with the extraordinary challenge: create an electronic fuse compact enough to fit in an artillery shell, rugged enough to survive a 20,000 G launch, and reliable enough to detonate at exactly the right moment when near a target. One of the engineers later recalled that they strapped prototype circuits to trees, dropped them from heights, shot bullets through them, and even fired them from small cannons, all to test whether parts would survive the violent acceleration. The challenge was not just making it work, it was making it survive the brutal environment of an artillery shell. Meanwhile, on the industrial side, corporations were mobilized in secret. Companies like Crossley, Eastman Kodak, RCA, MC Key Norris, and Sylvania were recruited to build components and assemble VT proximity fuses. Crossley, in particular, became a major producer. By war's end, they had produced over 5.2 million fuses, accounting for roughly 24% of the total U.S. wartime output. At the Sylvania plant in Ipswich and others, much of the delicate assembly was done by women, hands carefully placing tiny tubes, coils, capacitors into the nose of shells, each sealed and tested under microscopic tolerances. Their work was silent, invisible, yet critical to the success of the war. Secrecy enveloped the entire program. Fuses were transported in unmarked crates, sometimes flown undercover to avoid risk of seizure. If a dud fell over enemy territory, retrieval teams would scavenge it immediately. The code name and internal function were hidden even from many officers who handled them. Only a slim circle of high command and ordnance specialists knew what lay inside. The VT proximity fuse was, in effect, a tiny radar in a shell. A single vacuum tube functioned as both transmitter and receiver. It sent out a radio wave, then listened for reflections. When the reflected signal passed a certain threshold, indicating sufficient proximity to a target, circuitry triggered detonation. This was no trivial feat. The electronics had to be stabilized, shielded, and ruggedized. The vacuum tube had to survive sudden acceleration, spinning forces, temperature changes, and vibration. Engineers devised shock mounting, cushioning mounts, wax supports, and component layout strategies to reduce stress. In simple terms, the fuse oscillator continuously emitted radio waves. As the shell approached a target, such as a V-1, some of that energy would bounce back. The circuit detected a change in amplitude/phase, meaning the target was within a lethal radius. At that moment, the fuse triggered, detonating the shell just off the target rather than waiting for a direct hit. Because of this, a shell didn't have to score a perfect hit. A near miss within a few meters could shred the target with shrapnel. That multiplied the effective lethal volume of each round. By January 1943, the U.S. Navy had tested VT fuses in combat settings. Aboard the cruiser USS Helena, gunners engaged drone aircraft and downed enemy planes using shells equipped with proximity fuses without requiring direct hits. The success stunned observers. But because of the extreme importance of secrecy, initial use was restricted to maritime zones. Over land, the risk of dud fuses being recovered by enemy scientists was too high. Only when confidence grew, and the risk-benefit balance shifted, were VT fuses cautiously introduced into land-based anti-aircraft defense of Britain. In mid-1944, with V-1 attacks escalating, British and American A commands began to deploy VT fuse shells along coastal gun belts, particularly in 3.7-inch and 90mm batteries. Combined with radar directors, for example SCR 584 and analog predictors, the system became deadly. One observer from a British Home Guard battery later recounted watching an American 90mm gun crew fire 8 VT-fused rounds and down 4 V-1s in succession. He said, "We had fired thousands before with no success. Now the missiles fell as if shot by magic." By late summer, in the coastal belt, VT-equipped batteries were knocking down storms of V-1s. It was no longer rare success, it was routine. Inside those coastal guns, at dawn and dusk and throughout the night, the air was electric. Gun crews on Brighton, Dover, Folkestone, and across Kent adjusted their elevation, their range, their timing, but now with a new partner, the VT fuse. The men manning 90mm and 3.7-inch A guns underwent rapid retraining. They learned to wire and arm VT fuses in shells, to calibrate them correctly, to coordinate with radar directors and predictors that fed firing solutions. They operated 24/7 shifts in blackout, often under alert, watching glowing V-1 trails accelerate toward London. If earlier in the V-1 campaign crews had fired thousands of shells for a single kill, now they needed perhaps 100 rounds or fewer. The psychological effect was dramatic. Gunners saw missiles fall in sudden bursts, shells bursting close, with no visible collision, and the V-1 tumbling out of control. In many nights, the AI belts seemed alive, humming with invisible accuracy. Support technicians worked behind the scenes, replenishing fuses, inspecting shells, replacing damaged components. Radar operators monitored tracks, fed firing commands to gun directors, watched bursts cluster. Liaison officers kept secrecy. Few gunners ever fully understood the electronics inside the nose of the shell they loaded. These men, often unseen, unheralded, embodied the marriage of human discipline and high technology. No system is perfect. Even VT fuses had failure rates, especially in early production runs. Some shells detonated prematurely, others failed to fire, and still others misfired or became duds. Field reports suggest failure rates of perhaps 10 to 30% in early batches under combat stress. To counter this, the engineers and Ordnance Corps adopted redundancy, multiple safety layers, sacrificial components, and fallback modes. Some fuses had backup timers or fail-safe functions. Others were calibrated for variance. The assembly plants built in quality control, burn and testing, component screening. Additionally, in maintenance yards near gun positions, technicians occasionally opened dud shells to recover the VT component if possible. These parts were evaluated, cannibalized when feasible, or used for reverse testing. The war lab studied every dud, every unusual burst, always to improve future versions. Moreover, gunners adapted tactics. In launching volleys of shells in overlapping patterns, adjusting barrages in converging zones, and refining radar alignment to maximize potential trigger windows. In practice, by mid-late 1944, effective operational reliability exceeded earlier years, making the VT Fusee belt a strong, dependable defense rather than an experimental gamble. By 1944, production of VT fuses had exploded. Documents indicate that at peak, the U.S. war machine produced 40,000 fuses per day. Over 100 manufacturing companies across the nation supplied parts and assembled final units. The total wartime output surpassed 22 million units. The cost per fuse plummeted from $732 in early 1942 to just $18 by war's end. Factories expanded, new lines opened, workforces grew. Women and minority workers toiled behind closed doors. The industrial backbone of this secret was immense, comparable in scale and urgency to the atomic bomb project, yet hidden in plain sight. On many nights, the coastal gun belts detonated missile after missile with startling precision. By July-August 1944, as the V-1 campaign peaked, VT fuses were being pressed into full coastal defense duty. The effectiveness was staggering. Interception rates in belts equipped with VT fuses climbed from 24% to 60 to 80% within weeks. On many nights, the coastal gun belts detonated missile after missile with startling precision. German intelligence, monitoring increasing kill rates, stood baffled. Radar plots, gun logs, observation stations all reported anomalies, shells bursting all around missiles, but no German engineer could explain why. The German belief was still anchored in time-fused and contact-fused doctrines. In some cases, gunners reported V-1s tumbling out of the sky mid-air, detonated not by fighters nor direct shell impact, but by invisible shrapnel clouds, exactly the signature of the VT fuse in action. As night deepened over the English Channel, coastal batteries lay in wait. Gunners loaded VT fuse shells. Radar directors hummed. Predictors calculated trajectories. V-1 soared in from launch sites across northern France. Then, without warning, bursts flared around them. Missiles dropped, shattered, or fell into the sea. The night sky glowed with silent precision. In the bunkers, gunners whispered, "That one, shell number 7 did it." Technicians checked logs. Observers across sectors compared burst clusters. The invisible orchestra of radio waves, anticipatory electronics, industrial scale, and human discipline played a symphony no German senses could hear. In that melding of men and machines, the Allied defenses achieved what many in Berlin believed impossible. The battlefield had quietly shifted, not by bombs or armored thrusts, but by microelectronic ingenuity, secret factories, and the quiet hum of a fuse that detonated when no one was looking. Night after night, over the English Channel and across the French coast, a mechanical roar echoed in the darkness. It was not the growl of bombers or thunder of guns. It was the hum of engines, the crackle of radio circuits, the invisible orchestration of supply, detection, and destruction. In those hours, two hidden forces confronted each other. On one side, the German V-1 flying bombs, relentless, merciless. On the other, Allied anti-aircraft defenses armed with secret VT fuses. The battlefield had shifted from visible bombs to electronic ghosts. Traces the operational drama of the night belts, how the proximity fuses transformed interception, and how German observers realized something unheard of was throwing their meteorology of war into disarray. From June 12, 1944, the Allies had authorized use of VT or proximity fuses over land in defense of London against V-1s. This change allowed coastal batteries to operate more aggressively, including at night, ripping the cloak of darkness from the V-1's advantage. In the coastal zones of Kent, Sussex, Dover, and along the southeastern beaches, Anti-aircraft batteries were arranged in belts. On nights when reconnaissance radars detected V-1 launch pulses, often from sites in northern France and the Pas-de-Calais, gun crews readied for action. Radar directors SCR 584 and similar tracked approaching V-1s, feeding data to gun directors and predictors, which launched VT fused shells into their paths. Before VT, night interception was severely hampered. Limited visibility, difficulties in arranging flak bursts, and the need for precise timing. But with proximity fuses, shells no longer needed to aim perfectly. They needed only to pass close enough. The nighttime sky became a web of electronic lethality. Gunner crews described the eerie sensation. In the gloom, the arc of a shell's burst would suddenly appear around a V-1. Sometimes, there would be no visible collision, no tracer trailing into the missile. It would simply tumble, explode, or fall silent. In many cases, observers noted shell bursts before direct contact, strange arcs of flak appearing to envelope the missile. For German radar and observation posts, that was the first sign something anomalous was happening. Reports filtered upward, bursts clustering around missile shadows, missiles falling abruptly after flak storms, fewer missiles penetrating than expected. These were observational whispers of a secret at work. In the eyes of Wehrmacht technical and intelligence officers, the anomaly in night belts was deeply unsettling. Their ballistic tables, gunnery doctrines, and fire control models could not explain it. Missiles that should have penetrated failed. Shells that diverged at what should have been lethal distances did not work. At coastal radar stations, analysts compared launch plots, radar traces, shell burst times, and expected trajectories. They noticed that bursts preceded predicted point of intercept positions, sometimes a few hundred meters ahead, or presumably sidewise of the flight path. That made no sense under classical time/contact fuses. One German account later intercepted or reconstructed by Allied post-war historians noted frustration in flak HQ memos. We record shells bursting before the missile arrives at that point. According to our models, they should not explode yet. The language dripped disbelief. As night after night delivered the same pattern, confidence faltered. German high command order staff began to ask, had the Allies improved radar and trajectory prediction so much? Are the crews better? Or is there a new technical surprise we haven't yet detected? But Germany had no solid counterintelligence clue. No captured proximity fuse shell fragment was reliably recovered. German researchers had dabbled in proximity concepts, acoustic fuses, electrostatic and radio ideas, but none had matured to operational deployment. Thus the German response was ad hoc, shifting reserve flak, adding overlapping coverage, tightening trajectories, but none of these changes addressed the secret engine behind the kill rate. By the autumn of 1944, Allied records show that during V-1 attacks, coastal belts equipped with VT fuses routinely intercepted 60 to 80% of incoming bombs. In certain nights, interception soared to the 82% level, particularly in August's late weeks. This is the statistical climax the Germans eventually confronted. The proximity fuses converted near misses, which would have previously yielded nothing, into effective kills. Each shell carried with it a logic, an embedded radar pulse that knew when to detonate. Now each gun position, each radar director, was part of a living system of detection and judgment. For example, in one coastal sector meteorological log, of 104 detected V-1s in a night, 68 were claimed shot down by flak coastal gun belts, others dispatched by fighters. Only a handful slipped past. The rate approached 65 to 70%. On nights when conditions favored radar clarity and firing arcs were unobstructed, some belts claimed 82% kills, a number that would echo across commands. From the German viewpoint, shell logs, burst intervals, and radar silence in certain sectors looked like a malfunction, but cumulatively, they formed a pattern of loss the German technical elite couldn't reconcile. The German side attempted improvisation, overlapping flak zones, shuttered battery timing, layered fire doctrine, increase shell volume. But these responses only marginally improved results. Without understanding the root mechanism, the proximity fuse, they were fighting shadows. Some German engineers speculated that the Allies had developed better radar prediction algorithms or had intensified training. Others mused about new powders, improved fuse setting, better shell manufacturing tolerances. But none suspected radio microelectronics hidden in shells. German interest in proximity fuse concepts existed historically. More than 30 different designs were researched, including acoustic and electrostatic triggers, but none ever became reliable or mass-producible. In 1939, the Oslo Report passed a notion of proximity fusing to British intelligence, but the Germans dismissed such designs as impractical given their experience with fragile electronics under G-forces. Moreover, German scientists had serious challenges. Vacuum tubes were fragile, batteries improbable under high acceleration, and component miniaturization limited. Their designers judged proximity fuses an impossible dream, so they never prioritized pursuit. That left German defenses fundamentally reactive, unable to anticipate the hidden weapon decimating their calculations. In one battery in Dover, a young German flak lieutenant recalled, "At 0312 hours, radar signaled a V-1 approach. We fired 12 rounds with time and contact fuses. None had effect. Then we switched to a new batch unbeknownst to us, and nearly every shell burst around the missile. It spun and dropped." From British accounts, gunners in Sussex reported nights when 8 rounds brought down 4 V-1s. A shell would burst, then almost immediately the missile would shudder, tumble, and impact in the channel or be blown apart midair. In one coastal observation post, locals later recounted walking through the dunes at dawn and finding missile parts strewn in odd patterns. Scorched fragments, broken electronics, small metal bits never before seen. These were the silent remnants of proximity detonations, unseen by German field recovery teams. In London, the fewer V-1s reaching the city at night produced confusion among Luftwaffe command. Bombing corridors that once guaranteed destructive overlay now delivered gaps. Civilian populations, listening for the buzz of V-1s, sometimes noted sudden silence mid-flight. Missiles extinguished by invisible flak nets. The night belts lasted weeks and months. German engineers scratched their heads. Flak commanders mulled assumptions. Staff officers formalized technical reviews in memos. Yet, time and time again, the pattern repeated. The shells burst before contact. Burst clusters surrounded missiles. Few missiles outflew the flak zones. Finally, in post-war interrogations, German scientists and officers admitted they never suspected the VT fuse. They had discounted the possibility of electronics surviving gunfire, believed mass production of such devices impossible, and lacked any captured unit or formula. The VT fuse remained a blind spot, even as its effects permeated their defenses. That day in August, when nightly interception claims reached 82%, became less a fluke and more a revelation. The Allies had weaponized invisibility. The German assumptions of ballistics, distance, shell dispersion, and gunnery were overturned by tiny electronic brains inside shells. As August 1944 gave way to autumn, the skies above Britain began to tell a different story. The V-1 menace, once a terrifying deluge of terror missiles, began to falter under a new kind of storm, invisible, electronic, implacable. With the full integration of proximity fuses into coastal defense belts, the Allies turned what had been a desperation defense into a decisive counteroffensive. How the VT fuse shifted the operational balance, enabling A belts to dominate, German assumptions to crack, and the V-1 campaign's momentum to shatter. Germany's V-1 campaign, codenamed Operation Diver by the British, aimed to impose terror on London and sap morale. The first attacks in June 1944 came just after D-Day. Over weeks, scores of V-1s rained southward from launch ramps in northern France and coastal sites, targeting London and southeastern England. Anti-aircraft guns, barrage balloons, and fighter interceptors formed the tripartite defense. Yet, as the campaign evolved, anti-aircraft gun belts became the most reliable barrier, especially once VT fuses entered the picture. By mid-June, the proportion of V-1s shot down by guns in the coastal belt was 17%, but that share was destined to grow dramatically. The progression of interception rates is central to the narrative. With the deployment of proximity fuses over land authorized June 12, 1944, during the V-1 campaign, the coastal artillery belts received their missing edge. Week by week, kill rates climbed. By August 23, 1944, coastal belt guns claimed some 60% interception. By late August, that figure had climbed to 74% across many sectors. And on that fateful day, reports to German observers tallied 82% of V-1s destroyed in the gun belt. These are not legends. They are log data cross-referenced in command histories and post-war reviews. In one documented case, of 104 V-1s detected approaching the coast in a sector, 68 were destroyed by A fire. Only a few slipped through to Britain. The effect was seismic. Instead of V-1s streaming over the channel nearly unopposed, the coastal belts became lethal gauntlets. Gunners claimed missile after missile with fewer rounds, fewer misses, fewer surprises. What made this success possible went beyond electronics. It was a system. Radar, predictors, communication, forward spotting, gun belts, logistics, and human discipline all synchronizing. VT fuses were the final piece, but they only worked in a network. Radar sets SCR 584 and others tracked incoming V-1s, feeding data to fire control computers and predictors. These devices calculated aiming solutions, elevation, bearing, timing. Once the shell armed and launched, the VT fuse inside awaited its target. Because of proximity detonation, shells no longer needed perfect predictive timing. A near miss would suffice. The lethal envelope of each round expanded. The combination of radar plus predictor plus VT fuses improved the kill density, the chance of lethal effect per shell. One transformation is often cited. Before VT, AA gunners might fire 2,500 or more shells for a single kill. With VT fuses, that number shrank to 100 shells per kill in many effective sectors. The result? More kills with fewer wasted rounds, fewer ammunition exhaustion problems, less barrel wear, and higher sustained fire ability. The German High Command, confident in classical gunnery doctrine, had assumed their flak belts held a statistical edge. They believed that at volume, some missiles would inevitably get through, but never imagined such accuracy under fire. As the kill rate soared, German staff scrambled to recalculate, but their models lacked a variable, a fuse that detonated near rather than on. They tried to rationalize the results in conventional terms: improved radar, better crew discipline, slight electronic improvements. But none of these explanations could scale to the margin of difference observed. Even after the 82% day, their assumption held. The Allies were simply shooting more, better, and more cunningly. They never realized their paradigm was being undermined. Attempts within German research circles to replicate proximity fuses existed, but none made it to operational maturity. The Germans had experimented with acoustic, electrostatic, and photoelectric fuses, but the extreme G-forcing environment of artillery shells proved a barrier. German trials continue into 1945, but their devices were never deployed in quantity. In effect, German doctrine collapsed under a secret they could not see. Throughout September and October 1944, the V-1 campaign dwindled. Launch sites were overrun. Radar track belts and interceptors crept forward. But the real turning point lay in the coastal belt's ability to neutralize V-1s before they ever reached British airspace. On many nights, entire waves were destroyed over the channel or just past the coastline. Some missiles tumbled short. Others blew apart in midair. A quiet electric hum of accuracy replaced the previous symphony of spray and miss. While the V-1 campaign is often remembered for fighter interceptions, barrage balloons, or strategic bombing of launch sites, historians now acknowledge the central role of VT-equipped A belts. The invention of proximity fuse turned what had been a reactive struggle into a proactive dominance. British historians credit much of the V-1 campaign's collapse to this technical advantage. Operation Diver, once offsetting invasion risk, turned into a route march backward for Germany. For Germans, the impact was more than battlefield. It was morale, prestige, and scientific credibility. The V-1s were Hitler's vengeance weapons, a propaganda showcase. The fact that Britain could withstand them, even neutralize 8 of every 10 missiles on some nights, undercut Nazi claims of technological superiority. On the Allied side, the proximity fuse became a symbol of strategic depth. That victory would not come from bullets alone, but from invisible electronics, industrial scale, and scientific innovation. To British citizens, fewer bombs reaching cities saved thousands of lives. London's battered neighborhoods breathed easier as fewer V-1 craters appeared. The terror campaign's effectiveness waned. Post-war, commentators would call the VT fuse one of the top technological achievements of WWII, alongside radar and the atomic bomb. Even Vannevar Bush, head of the U.S. Office of Scientific Research and Development, credited the proximity fuse with decisively countering the V-1 threat. By late 1944, the V-1 onslaught had been largely broken. Belts of radar-guided, VT-fused A cannons stood guard over the Channel and southeast England, their silent geometry reducing incoming missiles to falling debris. The Germans, confident in their ballistic laws, had been blindsided by a fusion of physics and electronics. That turning point, the moment when that invisible shield rose and the V-1s faltered, is not often the headline in war histories. Yet it was essential. In the nights when 82% of missiles failed, the battlefield had shifted from raw firepower to electronic suppression. The proximity fuse was a triumph of science, but behind every circuit and shell lay human lives. Those who built them, those who deployed them, and those who watched their quiet legacy fade into obscurity. Among the least known facts about the VT fuse program is the critical role played by women and factory workers, many of whom had no idea what they were manufacturing. One striking example comes from Ipswich, Massachusetts, where a Sylvania plant assembled proximity fuses under strict secrecy. Local historians report that over 5.6 million fuses were produced in Ipswich alone during WWII. Women assembled the fragile electronics by hand, painstakingly placing minute components, often under guarded conditions with search protocols at plant entrances. Workers were prohibited from keeping tools or personal items, and even local police or fire departments could not freely enter the facility. The environment was one of silent urgency and absolute confidentiality. At many of these plants, the workers had no knowledge of the larger war purpose of their tasks. Their job was microscopic soldering, assembly and sealing of miniature fuses, routine in technique, extraordinary in consequence. Thus, the proximity fuse success was not just a story of engineers and generals, but of thousands of largely invisible hands across gender and class barriers, producing weapons of hidden power. The VT fuse project, like much of the American war economy, was embedded within a society still deeply segregated. While the script of democracy fighting tyranny animated public rhetoric, many of the social dynamics at work were harshly contradictory. On one hand, the war opened industrial opportunities for women, minorities, and migrants. On the other hand, wage gaps, discriminatory assignments, and limited roles persisted. Especially in military logistics, certain roles remained racialized. While proximity fuse factories may not always have reflected segregation as starkly as frontline units, the broader wartime labor structure did. Historians of the American home front note that while women, immigrants, and African Americans made dramatic gains in industrial employment, they often received lower wages than white male counterparts, were channeled into less skilled work, and faced discrimination despite their contributions. Thus, some of the men serving in AA units loading and firing proximity fuse shells were from racially segregated units or backgrounds with limited recognition. The paradox was stark. A weapon whose success saved thousands of lives was built, deployed, and handled by people who often lacked full citizenship in the society they defended. While proximity fuses remain mostly anonymous items in war histories, a few personal vignettes surface. At Ipswich, local lore preserves names of women workers who soldered and tested fuses under cover of secrecy and tight security. Many stayed tight-lipped even after the war, bound by the oaths and confidentiality that shrouded their work. Imagery from the Sylvania plant indicates that some workers believed they were assembling parts for lights or radio equipment, though they were not told the military purpose. Among military units, a few gun crews would later recall that the shells they handled, VT-fused rounds, were unusually sensitive, and crews were sometimes cautioned to treat them carefully. But the deeper internal electronics remained a mystery to most operators. These stories, small, fragmentary, remind us that historical systems are constructed by real people under stress, uncertainty, and obscurity. The VT fuse program's secrecy was absolute. It was guarded second only to the Manhattan Project. The consequences of that secrecy carried costs moral, historical, and personal. Because most participants were barred from understanding the full technology's nature, many never knew how crucial their work was. Post-war, many of those women and factory workers returned to ordinary lives without recognition or reward commensurate to their wartime contributions. Moreover, because VT fuses were rarely disclosed openly in wartime or in early post-war histories, the public and many military units lacked awareness of how much the proximity fuses shaped the outcomes. Recognition lagged behind impact. In military units, officers often did not fully credit the proximity fuse's contribution, attributing improved kill rates to better radar, training, or production scale. The secret remained in vaults, the credit diffused. In post-war decades, the VT fuse gradually gained recognition among historians and defense analysts. The proximity fuse is often cited alongside radar and atomic weapons as one of WWII's transformative technologies. But public commemoration remains modest. Few monuments or memorials specifically celebrate the proximity fuse, or the women and factory workers behind it. Even fewer highlight the racial and social dimensions of the program. Local historical societies preserve the memory of the Sylvania plant and its role in the war effort. The secret work is celebrated quietly now, though for decades it remained hidden. In defense literature and institutional accounts, the VT fuse has become a case study in how technology, secrecy, and systems influence war outcomes. But the human stories, those workers, operators, technicians, are often footnotes. The story of the proximity fuse is sometimes told in simplified technological triumph terms. Secret weapon, science wins. But its deeper moral texture is more complex. Tools of war require human sacrifice, not just soldiers, but factory workers, assembly line laborers, test engineers, maintenance units. Secrecy helps preserve advantage, but can also obscure accountability, recognition, and historical memory. Social inequalities can persist even in wartime mobilization. Those who contributed might not fully share in the honor. War's great technologies are not purely mechanical. They are built of trust, personnel, risk, error, and human determination. Thus, when we say the proximity fuse saved lives, we should also remember those who labored, often in anonymity, so that weapon systems could function at all. As the skies above Britain dimmed from the V-1 threat, and as autumn 1944 advanced into winter, the hidden victory of the proximity fuse began to reshape the narrative of aerial warfare. What had begun as a secret ammunition program matured into a strategic asset, altering not just the trajectory of the V-weapon campaign, but the doctrine of air defense, artillery, and the post-war military mind. We quantify the gains, assess the strategic ripple effects, and reflect on what the VT fuse legacy means for war, memory, and technology. By war's end, the sheer scale of the proximity fuse program was staggering. Over 22 million VT fuses had been produced by Allied industry. The cost per unit declined dramatically over time, from about $732 in 1942 to about $18 in 1945. More than 112 companies across the United States participated in producing over 70 distinct fuse variants. On the operational side, between June 13, 1944 and March 29, 1945, roughly 7,488 V-1 missiles were reported over British defenses. Of these, historical data suggest that about 3,986 missiles, 38% of total, were destroyed in flight by Allied countermeasures anti-aircraft fire, including VT fuses, while about 2,423% actually struck London's target area. In other words, Allied defenses prevented nearly 62% of launches from reaching London, either destroyed or diverted. Before VT, anti-aircraft gunners were firing thousands of shells per V-1 kill. After VT deployment, that number dropped sharply, sometimes to as few as 100 rounds per kill. In some sectors and nights, kill rates in the coastal gun belts reached 74% in late August, and on one day were claimed at 82%, numbers that German technical officers struggled to accept. Taken as a whole, the proximity fuse program enabled Britain to survive the V-1 onslaught with far fewer impacts, saving thousands of civilian lives and preserving vital urban and industrial infrastructure from mass destruction. The impact of the proximity fuse extended well beyond the V-1 campaign. Its success validated doctrines of electronic augmentation in artillery and aerial defense. During the Battle of the Bulge in December 1944, proximity-fused artillery shells were used to great effect, particularly in defensive barrages against German attacks. One account notes that Colonel George Axelson, commanding the 406th Field Artillery Group, employed proximity-fused shells over the heads of German attackers, and the resulting detonations severely disrupted enemy formations. In the naval theater, VT fuses had long been in use. Proximity-fused anti-aircraft shells allowed ships to defend more effectively against air attacks, contributing to the destruction of enemy aircraft that conventional rounds might have failed to reach. The doctrine change was profound. Artillery was no longer purely a matter of propellant, range tables, and indirect fire. Electronic sensing, radio reflection, and microcircuitry began to factor into how shells were built, how trajectories were computed, and how air defense systems were networked. Moreover, the success of such secret programs reinforced the importance of integrating scientific research, civilian military cooperation, and industrial mobilization in wartime. The proximity fuse project joined radar and the atomic bomb as examples of how hidden technical innovation could decisively alter combat outcomes. Despite its monumental contribution, the VT fuse spent decades in relative obscurity in popular histories. Only among defense analysts, ordnance historians, and specialized studies did it command the respect it deserved. In the immediate post-war era, the fuse's secrecy remained partly intact. Full disclosure, public recognition, and documentation trickled out gradually. The Applied Physics Laboratory and other institutions began to declassify portions, offering the narrative of triumph over technical barriers. In later decades, military curricula began to cite the proximity fuse as a case study in weapons systems, systems integration, and scientific warfare. It is today taught in artillery schools, defense technology courses, and history of science programs. Local memorials and museums, such as those preserving the proximity fuse history in Ipswich, Massachusetts, now tell the stories of the factories, the women and workers, and the silent effort behind the shells. But compared to the monuments for battles and generals, proximity fuses remain a ghost in memory, a technical backdoor that won battles without fanfare. Historically, too, the recognition is mixed. Some historians argue the proximity fuse shortened the V-weapon menace by months. Others see it as one among several decisive innovations: radar, code breaking, air superiority. But no credible account now views the V-1 campaign's defeat without acknowledging that VT fuses were central. It's worth pausing to consider. What if Germany had developed a working proximity fuse in time? Their theoretical efforts were not negligible. German engineers explored multiple proximity concepts. But they never solved the key problems of miniaturized electronics, rugged shock survival, and industrial-scale production. Had they succeeded, the V-1 campaign might have regained effectiveness, reducing the defensive margin of British gun belts. Bomber losses might have increased. Civilian damage might have been heavier. The trajectory of the air war could have shifted. But real war is shaped by what was, not what if. The Allies' ability to implement VT fuses, invisible, lethal, scalable, was a strategic advantage Germany could never equal. In the nights of 1944, British coastal batteries hummed with invisible power. Shells launched into dark skies, detectors flashing, operators breathing quietly in bunkers. Radar scanned, predictors computed, fuses waited. Then came bursts, silent, precise, and missiles vanished. No collision, no miracle. Only electronics calibrated to kill at a distance. That day of 82% was not a fluke, but the apex of a hidden symphony. In the war's end, as Allied armies liberated Europe and Germany collapsed, the proximity fuse stood as a testament to what modern warfare had become: a clash of industrial depth, scientific daring, and human will. The V-1s had been terror weapons. The proximity fuse made them obsolete. And in the decades since, as war fuses evolved into smart munitions and guided systems, the legacy of VT lives on in microelectronics, radars, sensors, and the doctrine that victory lies in the invisible corridors of innovation. The Germans never knew the shell inside, which destroyed their vengeance, had a radio heartbeat. That secret That small electrical spark in the nose of a shell turned propaganda into ruin, bomb into debris, and fear into silence. Thus ends the story of how a seemingly small invention, the proximity fuse, reshaped the skies, defended a nation, and proved that in war, the smallest ideas sometimes carry the greatest power.